Yeah, hello everyone. Uh, okay. So today's topic for ACSL class is a priority queue. And if you don't know what a priority queue is, but you've heard of a heap, they're very similar. Okay, so first, to understand what a priority queue is, we need to recall what a queue is. We need to know what a queue is, which basically is a first in, first out. Meaning if I add A and then I add B and then I add C, then I take A out, and then I take B out, and then I take C out. So into NQ or to push is to add an island to the queue. Let's say we had a queue here. To NQ the other A, we we would just add A here. And it's and then to NQ B would add B behind it. And to DQ, we remove the oldest item in the queue and return it. Like, or basically the frontmost item. So if we were to DQ, we would remove this item and return A. But this leaves us two problems. So first is, let's say we had a line of people here, and let's say the person 5 is decides to cut the line, and so they move here. Currently our queue has no method of doing this. And the second problem we have is, let's say we have 4 tasks that are due within certain days. First, let's say like we have A, which is due in 2 days, B, which is due in 3, C, which is due in 1, and D, which is due in 4. If we added it in this order, we would have to do A, B, C, and D. But since C is due the earliest, in reality, we should be doing C, A, B, D. And these two problems are basically, to solve these two problems, we use a priority queue. Okay. And the other portion we need to learn about, to know about a priority queue is a binary search tree, since that is how a priority queue stores its elements. So basically, remember that a binary search tree has the key for each node has a key, a pointer to the left child, and a pointer to the right child. And that a key at every node is always greater than or equal to anything to the left. It is always less than the key of its right. So now we've also learned how to add a task to a tree. We would add it to, let's say we want to add another A, we could just look A here. And so to review, to find the next highest priority task is to just look at the one to the right child. If that doesn't exist, this is the highest most priority task, which gives us the answer to the second question, as we we continue going right until we see a node that does not have a right child. That node will have the highest priority. Okay, so basically our initiative with different types of data structures. And so array list, and we need to learn how to insert slash delete and which ones to delete. Array list is to remove an item at an index. Let's say this was index I, but then it may be time costly as all the elements to the right of the index will all the elements to the right of the index will have to be shifted over by one. And the stack is first in first and last out, meaning if we have 3 tasks, we can only take the top one out, which means we can't access the bottom ones. For a normal queue, if we had this, we always remove the frontmost element, which was least recently added, or the oldest one, and we cannot access anything in between. And to a binary search tree, we remove an item by searching the tree. Like if we were to look for K and K was here, we just search the tree and find K. And priority queue in a heap is most best at removing the largest or in some cases the smallest item. So there's many uses of a priority queue, such as like a event-driven simulation. A customer is in line, and this front node is always going to be min or max. And the two children nodes are always going to be larger than or equal to it. Uh, and then budget planning, like what to buy, we can sort it on importance. This problem has not appeared recently. Any type of problem relating to a priority queue has not appeared, wait, has not appeared recently on any of the tests, but it's one of the topics ACSL has. And it's better to be prepared for it and get the question right than not know what a priority queue is. And then task planning is we can have like a step order, and this is especially useful if the steps are given out of order. And then budget planning is like what to buy, like importance of what to buy. Like you need food a lot more than, let's say, you need money to buy a phone. And these are just mainly applications, like when you would use them, but usually, I'm not exactly sure, but usually these problems should be just uh like, okay, so they give you a string to put in the priority queue and asterisk, meaning that you will remove an element and then they just want you to and return it, and they just want you to see the output. It's usually, these are mainly real world situations which a priority queue could be useful for. And then you can use a priority queue for Dijkstra's and Prim's algorithm, both of which you may learn later in computer science courses, and operating systems. Like, let's say you find your computer crashes because of 3 bugs, and one of them caused the others. And basically, we just need to know the importance of each bug, especially if the we need to know the importance of each bug in order so we know which one will fix, as well as which one will cause the most impact if not fixed. And basically, anything that you need to get the minimum, the maximum, or a priority of, you can use a priority queue. So uh, a binary tree is empty or nodes to the left and right. Not all of them have to be filled. But then a complete binary tree is one that has every single level except the bottom one filled. And the height of a tree with n nodes is always log base 2 of n. Basically 2 to the power n, sorry, 2 to the power of height. So this is 2 to the power of height gives you n, but these are very similar, but you can't have decimals. Decimal heights. Height will always be an integer. And the height only increases when n is the power of 2. As shown with n equals 16, we have one extra node. If n was not a power of 2, like 15, if we completely disregarded this node, we would have 15 nodes. They would still have a height of 3. Okay. Priority queue is similar to a binary search tree, but you can only delete the smallest or largest item and retrieve the smallest or largest item. Like in a priority queue, when implemented, may look like this, but we will only actually have access to this. And inserting and deletion will be done in guaranteed time. It will always be log up at most log base 2 of the height. Sorry, not log height, log base 2 of the n, the number of elements. And getting the smallest is always going to be done immediately, as we can just access the top element. And then usually there's a minimal priority queue, which all the elements below are larger, and a max priority queue where all the elements below are smaller. And if we're talking about a minimum priority queue, every single node has to be less than or equal to both of its children. Or if we're talking about a max priority queue, it has to be larger than or equal to. And in order for a priority queue to fully work, the resulting tree that we build using it has to have no holes. Like this tree does not work, as there are 2 holes here. But if we were to fill that in, this tree would be complete. So in order to add to a priority queue, we first put it at the bottom. So, and then we make exchanges with this parent until the tree is valid. So like an example would be, we have a priority queue of American, which is right here. And then we insert C. The insertion position first goes here. And then we look at C and N. And the problem is that N is greater than C. So we have to switch the 2 elements. So this becomes C, this becomes N. And then we look at C and I, and we see that it still doesn't work. So we have to add C here and I here. And that results in the American. So do you guys understand everything so far? Okay. We always add it to the next available position. So like if we had C, we always add it here. And we only swap it with its parent if it is smaller. Okay, Zixun, can you clarify your question?
Like, what if one of the letters for like both, like NMEC or something, like which side do I put it on?
Wait, which letter?
Like, if in some situation, like one letter works for like all of the letters that we have now, like which one do I have to put it under?
We always put it at the next available position. So the next, like, it'll always be a bottom row with some elements filled, or somewhere 0 elements filled. Like in this case, we have R here and nothing else. So we always put it next to R. It may need to go to the next node. If this was, let's say, X, it might need to go to this node, but it always goes to the next available position. It always go there. So an example of this is we have this uh, priority queue, and we need to add S. So first, we add it to this position, as that's the next available position. However, this fails. And in this case, this is a maximum priority heap, which is the largest letters on top. This fails because S is greater than H. So these two swap. And then so this is H, this is S. These two also need to swap since S is greater than P. So this will be S, P, H, which is which is our answer. And then so to remove from a priority queue is to remove the maximum number. And to remove from a minimum priority queue is to remove the minimum number. And so if we were to figure out the minimum number in a minimum heap, where is that position? Please put your answer in the chat. Okay, it seems like you guys are still a bit confused as they didn't get any answers, but basically a minimum priority heap has the minimum element on top. If this was 1, these two have to be greater than or equal to 1. This 2, this could be 1 or it has to be greater than or equal to 1. Oops. Okay. So all the elements have to be greater than or equal to the. So the minimum number in the minimum heap is always going to be at the top. And then the next question will be, are we allowed to remove it? And why or why not? Okay. I guess uh, if we're given a heap, we can technically remove it, but not directly. Because after we remove it, let's say we had a heap like this. Sorry for the background. If we remove the top node, this is no longer one heap, this is splits to two. One of these two. So in order we can remove it, but we have to move something up to here in order to do it. So to delete it, we can only delete the smallest or largest value. We have to replace the top node if this if it's like this with the bottommost and rightmost element. So after deleting this, we have to take the bottommost and rightmost, which is this element, and move it up to there. And then however, this usually results in one of the smallest letters taking taking this tree will no longer be a heap, and in order to do that we have to then compare it with its two children until we see that it is in a valid position. So like an example, we remove T, then we remove H, we have to move H up since that's the bottommost and rightmost. And however, this we can see this violates the order as H is smaller than S. So then we swap. So this becomes H, this becomes S. And then we see that this violates both positions, both as still. And so we can technically either swap here or here. But in this case, if we did swap here, this would result in uh, P and then H. Or if we swapped it the other way, and then this is H, then this would result in N, and this is H, and H is greater than I and E. Okay, so first priority queue problem is to create the priority queue of computing. And what letters are in the bottommost row? So if we were to, bottommost row would be the last row, like this one in this case, from left to right. Okay. Yeah, this is you're correct. So first we have to do it. We do C, and then it's CO, and since we always fill in the next available position. Uh, CO and then COM, since M is the next available position, and then we add P, so P is goes there as that's the next available position, and then U, and then T, and then we have I. However, if we were to add I here, it violates the conditions of the binary search tree. So we have to swap these two, which is why how I ends up there. And then we add P back, we add P, we add N, and N is less than P and O, so N goes there. And then we do G, and G goes up there, and we're left with P and O on the bottom. Okay. We have a second one. We have to create a min heap with the letters in the word programming. And we need us to find the letters in the bottommost row from left to right. Okay. Uh, almost, but not correct. Okay, so programming the tree will result like this. So we start with P, and then we add R, and then we add O. But then these two need to switch. So then we have O and P. And basically, to make sure, since ACSL, the usually is going to partially will be multiple choice, but just make sure, so we have programming as 1, 2, 3, 4, 5, 6, 10, 11 letters in the, we have 11 letters. So they're always, and the power to that smaller than 11 is 8, which means for the rows above it has 8 minus 1 letters total for all the rows above it, which is 7, which means you would have 11 minus 7, which is 4 extra letters in the bottom row. So make sure you get the correct number of letters in the bottom row. Okay, third question. We have a oops, that's not supposed to happen. Okay, we have priority queue. And a letter here means insert, and an asterisk means to remove. And we are given initially empty. And we need to get the sequence of values returned by removing the maximum operations, which basically means this has to be a max priority queue. Okay. Uh, let's solve this together. So we've priority queue. So we start with P. No, I should do it. I'm gonna do it sideways because we have room sideways. So R. Wait, no, let me just do it normally. Sorry. So P, then R, and then I. And then I is, since this is a max weight, okay, this should switch. So this should be RP. And then O. And that's so far correct. And then we do a removal. So we remove R, and then we have to move O up. And then we have to switch the O and the P to make this a heap again. So this is O, this is P. And then we add a R again. So then it returns to its R there. Oops, this R should go here. And then R is greater than P. So eventually, basically, R does this, and I does that. And then we remove it again. So then this R goes away. So the R, and then we remove again. So then this P goes away. Wait, sorry, why is it not? And we're left with O. And this, no, okay. And then we're left with O. Right, attached to an I. And we had added a P. And then we add I. So I must go here. And then we pop the I, so the O. So this is O. And these two, one I will always be greater than the other. So this move the I up. And then we add a T. So we add a T here. And these two have to swap. So T goes here, I goes here. And then we have to remove the T. So T does that. And okay, basically the bottom rightmost letter goes up, and then goes after we remove the bottom rightmost letter goes to the top, and then we have to do swapping in order to make it a priority queue still. And then we Y will go there because we would add Y, attach it to the I, and then pop it. So that happened. And then we pop the two I's because there's two elements. So we pop I and I. And then Q, and then U, which is larger. Wait. Yeah, so U is larger and E. And then we pop them all. So it goes U, and then Q, and then E. And then we add a U and remove it. So we put a U, and the last, no, that's not, the last E stays. So eventually our final tree will look like this. And the answer should be RPOTYIIUQEU. Okay. So do you guys have any questions on priority keys? Okay, if not, that's going to be all for today. You guys are all free to go.
Thanks.